Log on, tune in, find out. Another good idea from Cambridge.
So this afternoon's speaker is Phil Rundell from Texas A&M.
Thank you. Thank you to the organisers for giving me the opportunity to talk to you. I made these slides up as a pastiche of various things, and looking over them the last half hour, I realised I missed out two things, that this is work with Rainer Kress and Martin Hanke. Okay, the title's not quite what I originally gave you. It's probably a little bit better, but that's okay. So here's the problem. It's on the board, and therefore it's two-dimensional. Two-dimensional is sort of important, but not completely. I can tell you as we go along when 3 will also work. But you've got an outside domain, and if I can find the laser pointer, the outside domain is something you can measure things on. You have in this case to start with, the simplest of all elliptic equations. You have Laplacian's, a steady state problem, and there's something inside. I'm calling it D with boundary gamma, and this is what you've got to try and find. Now, of course, if you knew the geometry, you knew everything that was here, then given F, you could find G or vice versa. But I'm assuming that the problem is overposed for a reason, and in fact, if you've got both F and G, as I'm now showing, then the discrepancy between the measured G and what you would compute putting in F tells you something about D. So this Cauchy data pair, I'm asking, what can you tell me about D? I'm going to change the problem several times throughout, and the bottom line is I care about questions of uniqueness and reconstruction methods. Okay? And sometimes uniqueness is clearly impossible. That is, I can't tell you everything about D, but I may be able to tell you something about, for example, its volume and rough approximation of where it is. And that could be useful in another context. Or it might be all you want, right? If you're looking at this as a model, for example, of thermography, looking for temperature distributions of something inside, then you want to know if something's inside and how big it is, for example, if it's a cancer. Is it a positive or a negative? If it's a positive, how big is the positive? That could be all you care about. And of course, we need to know something about what we're looking for, because otherwise there's no hope here from this problem. And of course, this is going to, oops, don't hit the button. Oh, I think I've hit every button under the sun. Okay. How much data are you willing to collect? If you give all possible Fs, complete set, measure all possible corresponding Gs, it's a huge amount of data. This surely gives you a whole lot more. And the answer, of course, is yes. In this talk, I'm going to make the assumption that you have only one measurement pair. That's it. So obviously, there's a limitation on what you're going to get out of it. So now, since we know the outside, from now on, the outside will be a circle, right? It's not, but we can simply say we know this. And let's supposing that I know that D is a conductor, a piece of metal, right, pure conductor lying in a conducting matrix. And you want to try and find what D is. Well, it turns out that for one Cauchy pair, right here, you can actually recover D by a quote straightforward home. I have to stop doing this, don't I? You went past about 20 slides here. So a so-called straightforward Holmgren example, which I'll show you later on actually how it works, says that you can actually recover the shape of D. Now U is harmonic all the way here, but it's not harmonic inside D. Well, it is for a small way in, And then there's an essential singularity somewhere and the solution blows up. Okay? So D must have an essential singularity in its interior, and that's an important point. If I've got a hole, and the hole means that the boundary condition on my thing D now means the normal derivative is 0. So I've got a cavity. How about detecting that? A little trickier, okay? But you can still do it from a single Cauchy pair. Now, if I've got two measurements, if I've got an impedance condition with the right sign, it turns out uniqueness is a lot trickier. In fact, a whole lot trickier. But in fact, with two Cauchy pairs, you can get both the parameter and you can get the boundary. And I'm going to come back to this. So you cannot extend U as a harmonic function into all the inside. There's a singularity, and this is what I'm going to be zeroing in on. Of course, I could have a conductivity that was 1 on the exterior, 2 here, so there's contrast. And again, I give you a single measurement and want to know if there's a possibility of recovering the shape from that. And of course, the answer here depends on what you put in, and I won't go into that anymore. Again, there's a transmission condition now across this, and there's a jump discontinuity in the derivative by my assumption of contrast. Again, a singularity inside, and any reconstruction method is in fact going to detect a boundary in some way or other by utilizing the non-harmonic nature of U there. Okay? Of course, we can do this with a completely variable coefficient. We can give you the entire Dirichlet to Neumann map, all F's and all G's, but that's outside of the scope. And notice in this case there is no singularities in the sense of what we've discussed before inside. Okay, what happens if it's a source? So I have in the interior here, Laplacian of U is some function, and Laplacian of U is 0 outside. This is a reasonable model, for example, for a tumor growth at a very base level. Tumors run about 2 to 3 degrees centigrade warmer than the surrounding tissue, although they're probably, for all intents and purposes, very close to the same tissue. And so can you detect this heat source by measuring the temperature and heat flux on the boundary? The answer in general is you can forget this, because, for example, if I just said that it wasn't located inside a D, it was a random function f, you might think there's a possibility of doing something here. There is in fact none. And there's none because you just take any function h at C2 with support inside, define f to be the Laplacian of it, and you'll see that it's got Cauchy data 0, and it's not the 0 thing, right? And what this says is that even, if I've got a function phi of phi x inside, again there's no hope. And there's no hope for the following reason. You can simply subtract off the data on the boundary, putting h as f, h harmonic, subtract it off, and without loss of generality, you can assume that f is 0. That means there's only one possible Cauchy pair you can give. And this works because this problem is linear in this unknown. That means there's no Dirichlet to Neumann map, and so you cannot get a function phi of x out. Right? So the question is, what can you give? And the answer is, I'm going to try and do this one. Laplacian U of chi of D. It's 1 inside, it's on, and it's off outside. In fact, you can prove uniqueness for this problem. It requires that the domain be star-like. You can actually, you can improve on this by making a finite number of regions, each of which is star-like and separated in some way. But you have to know that it's 1 inside and 0 outside, and not something you don't know inside. Okay? Another problem which is now coming down, we're coming down the chain in some case now of easier problems, is supposing the sources are simply, as I've got in the red, monopoles or even dipoles, point sources. Now, the problem actually is quite easy, and I'm going to show you how easy this is and how you actually compute this shortly. And, of course, a continuation shows you that the location of these poles is easily determined. Why is that? You've got on the outer boundary a harmonic function. So stick it into the complex plane. These poles must be the roots of the, must be the residues, and use Cauchy's theorem. Okay? Of course, I could have multiple regions, and that's what I'm caring about. I care about multiple regions. It's also possible to measure only in an arc, and you'll see that in theory that doesn't hurt you one bit, but in practice it does. I'm going to show you a reconstruction later on of several things like this, but if you like the number 100, well, first of all, the condition number of the problems I'm going to show you is around 10 to the power 4. Okay? That means that if your data is decent, you can invert the matrix. What if you only gave me the thing on a small arc? Then the proof I'm about to show you will still work. Supposing the arc was only, for example, 2%. The proof of uniqueness will still work. The condition number now goes up a little bit. It's more than 10 to the power 100. Okay? There is a complete disconnect between uniqueness on the one hand and two, your ability to reconstruct. Okay, there could be cracks. And a crack, of course, can be insulating or it can be conducting. And in either case, there's a jump across the crack, and there's a crack tip singularity, which is a square root. Once again, you might want to try and determine the crack by looking for a singularity. I was talking about essential singularities for the other one. I was talking about poles, and now we're talking obviously about the branch cut singularities. I'm not going to pursue this any further. It's not that I can't have any interest in it, it's just that I've got no idea how to do it the way I'm going to show you. And finally, on this set, scattering. The classic scattering is you've got either a point source or a far field pattern coming in, plane wave, hits the object, bounces out, and you measure the reflected wave u infinity at the far field. You can convert this also, if you want, to near field Cauchy data. Near field, by the way, means that you're within about 3 or 4, maybe 5 wavelengths of the scatterer, and after that you're really pretty much near the far field situation. And this is a classic problem, and the problem is to recover d from the far field u infinity. And again, I haven't quite told you what d is. I will. And of course I can look for not only d being an obstacle, but it can be a source, and that's what I'm going to be talking about later on in the talk. Okay, for those who haven't seen it, every talk should have a sort of a detailed, quick, simple, nice, enlightening proof. And I apologize to those who, for this is well known, but for those it's not, it's a take-home. Okay, let's suppose there's two obstacles, D1 and D2, and they're both conductors, perfect conductors. So I have this situation. I get data, f and g, for both my functions, u1 coming from D1 and u2 coming from D2. So if I subtract these, then what I end up, oops, let me go back, it's too much in this one. If I subtract u1 and u2, then u1 minus u2 is 0 Cauchy data on here. But it's also analytic, or it's harmonic. And so if it's 0, by Holmgren's theorem, everywhere it's analytic, it must extend in as a 0 function. So in particular, it must hit D1 and D2 union boundaries as a zero function. Okay, so I've got U1 was 0 on here, originally U2 was 0 on here, and the difference is 0 on here. So that means that U1 and U2 is 0 here, and U2 and U1 is 0 here. Okay? So I've got that. Now, look at the picture coming from this region. D1, not D2. That's what I've got. Aha! U2 is identically 0 on that boundary, and since U2 was defined everywhere except for D1, which was over here, this means that U2 must be the zero function. But if it's a zero function in an open set, it must be 0 everywhere, including out to the boundary. So the data you gave me was 0. Well, that's not allowed. I mean, you have to give me non-zero data. So that says that this is impossible. This region cannot exist. So there's no such thing as D1 not D2, and therefore D1 intersection D2 must be empty. Okay? You can almost do the same thing for the whole, but you've got a cusp here. And there's a technical problem with cusps and Neumann data, but you can get over this. If you try and do the impedance case, you have a problem. You've got an outer boundary here, derivative, and an inner boundary from the two subtractions of the geometries, one from D1 and one from D2. And for uniqueness, which you could then, of course, also try with the same trick, you've got one normal coming in and one going out, and that direct problem doesn't have a unique solution. So you really can't prove it by the same trick. But surely, if uniqueness holds for Dirichlet and it holds for Neumann, it holds for in between. I'm going to give you alpha, right? Come on. That has to be the case. So if you go into R3 and take a ball of radius r, and Laplacian u of 0 outside that ball, give data on the outer boundary. This boundary condition is the one we had. Then here's the theorem. Choose your favorite large integer. Okay? Pick any two numbers, R1 and R2, any regions you want, any one you want. Okay? There's an alpha such that the problem with R1 and alpha has the same Cauchy data, all n pieces, not just one, all n pieces, as the region with R2 in that alpha. And so basically you can make the non-uniqueness set as large as you want. And these are only circles. So spectacular failure. Amazingly, if you give two pieces of Cauchy data, one of them strictly positive, the other one linearly independent, this counterexample disappears and you've got uniqueness. How about the Helmholtz equation? Well, it's problematic except for small enough k. And I'll show you the whole slide. You get exactly the same thing. Everything works, but you get the Helmholtz in here. Now, if you can avoid kappa or k being a Dirichlet eigenvalue of Laplacian, minus Laplacian, you're in good shape. But you don't know that, right? Now, what you can show is that if your region is small enough, okay, or your wavelength kappa is small enough, then there can be no eigenvalue, because you know the first eigenvalue of Laplacian is about 2.4, the 0 of J1, right? So if you're avoiding that, then you're in decent shape. And if I'm in a unit circle, for example, then any inclusion has to be less than 1, so that works. So for a large amount of what you might be talking about, unless you make the frequency high enough, then you don't have a problem about uniqueness, but otherwise you do. This is one of the great open conjectures that any kappa works from one incident field, okay? And it's completely open in the general case, although there's been many little restrictions added that seem innocuous, under which you can prove uniqueness for the thing, but without having one of those restrictions, it's still open. So how about the source functions case? As I said, if D is star-like, you're in good shape. Otherwise, some reasonably minor assumptions, which you have to make, of course, is that uniqueness also holds. So this looks good. And here's what I want to be able to do. First of all, instead of detecting the boundary of D directly, I want to determine the singularity of the mnemonic function that matches that Cauchy data. And then, maybe these singularities can give an indication of location of region D. I know the singularities have to be inside the thing. And that's useful. And of course, if I've got 3 or 4 objects, that could be quite useful. And then, maybe better, maybe I can translate the singularity information coming from the Cauchy data into the geometrical shape. Now, even if I can't do this, and I realized again when I was checking things over that I'd missed out one transparency. I'll try and draw it for you. Let's supposing I want to do this in a traditional way. The traditional way says you guess the domain D, you take the map psi that takes the domain D onto the Cauchy data. It's non-linear, but it's unique, so you can calculate its Fréchet derivative quite easily, and you use Newton's method. This works. Not only does it works from one set of Cauchy data, and it gives you the very sharpest reconstructions of any method I know. Now, let's supposing that I had an obstacle that looked like this. And you'll see this obstacle later on. And it's that big. I'll schematically give you 2 examples. One is a function that looks like this, and the other one is an ellipse that looks like this. Now, you would have to say that either of those 2 things are decent starting guesses. Unfortunately, my favorite method disintegrates rapidly. This is not good enough starting guess. So the problem with a Newton scheme is you need a really good starting guess. And without that, it doesn't work. Now, as you get more and more data, that is, you give more Cauchy pairs, you can make things a lot better. And that's why many of the other schemes that use multiple data sets are very much more stable. Okay. Now, and the continuation. I'm going to be using it left, right, and center. It's very powerful to use this technique for uniqueness theorems. You've seen one already, and many of you are in Edinburgh, and if the theme of Edinburgh was, I can put it in a couple of words, uniqueness theorems using analytical continuation. Probably not incorrect. And for uniqueness theorems, yes. But reconstruction algorithms, this can be misleading. And in fact, it leads to one of what's sometimes called inverse problem crimes, the representation theorem. I have a representation theorem, and therefore I have a valid reconstruction method fallacy. So I want you to meet one of my co-authors, Rainer Kress, for those who haven't. He actually, I think, coined the phrase originally inverse crime. And here's Rainer demonstrating what happens when you perform an inverse crime. So here we go. Here's Rainer, and here's what we want to try and do. You only see his head. I want to show you the rest of Rainer's body, and how I'm going to do it is draw a circle around Rainer's face like this, and feed it into my tested and true analytic continuation solver. Now, we tried several reconstructions. Some I really couldn't show you the pictures of, but here's one that I liked. And Rainer liked it too. But in fact, for those who don't know, this is actually a monument to failed analytic continuation reconstruction algorithms, and I'll show it to you now. It's a picture of it. It's this. Okay, humor aside, let's look at the source problem, which I promised you earlier. I want to recover an f, and if I only assume that f is pretty singular and it's got a support within my domains D, and remember from what I said, you can't expect any sort of unique determination of f here, then what you can do is write the thing in terms of Green's functions. You can write out the main term in terms of this Green's function, and you can see what you get. You basically get logs coming from that singularity, residues lambda, and poles zj. And if you continue this process on, running your data f out the way, the Cauchy-Riemann equations converts that data into values of that function, and you can end up with an expansion in terms of the radii, and if they're less than 1, as I'm assuming, you can get an asymptotic expansion that goes on and on and on. And the first residues gives you the mean of my f over the domain dj. And the next one up gives you the centroid. So it's possible to pull out some information here, even though you don't have uniqueness. Okay? So the coefficient of the power series here give the moments of the source, and how well you can do this depends on how small your regions are. Okay? If I differentiate the harmonic function that I get out of replacing the Cauchy data harmonic function by an analytic function, then again I'm running it out now as a series of residues, monopoles, dipoles, and so on. And when you do this, you see that the residues in fact are the area of dj, and this is the centroids. Now this could be just all you care about. Even if there's a variation in the domains, you want to know, it doesn't tell you how many there are, unless you can do that expansion, of course, fairly well and recover what m is. But if you can recover m, and you can recover these points reasonably well, and these residues, you get locations, number of objects, and you get some sense of the size and some sense of where they are, the centroid. I'm going to write my data G as alpha k. So every time you see alpha k from now on, it's the Fourier coefficients of my data. And what I'm going to do is take that Cauchy data and say it's an analytic function goes into the interior. I want to make an approximation to it. And that approximation I would like to choose is a Paddy approximation of degree p upon q, their degree up to 2m. And which one I choose, of course, will give me a different answer. Right? We'll talk about this in a second. Now you can compute Paddy's in essentially lots of ways, but 2 ways is the L2 norm, most common, or you can do it in the L infinity norm. It's a little more complicated, and it depends what you're looking for. I'm going to use the L2 case, and it certainly gives me information about the moments. So if I've got point sources now, then I've got Sk is the location of my pole, and lambda k is a residue. And I'm looking here at the case, for example, it's monopoles. How would I reconstruct the function f from the data G? That is, how would I get lambda and Sk? Okay? And who cares? Well, I'm going to tell you that the problem this is the bottom line of the talk. The problem I really want to solve is the case when I've got multiple sources that are some geometrical shape. I've got several of them. I've got an analytic function outside of that whole thing. And the question is, what happens if I take that analytic function on the boundary where I've got the data and write it as a Paddy approximation? The answer is, I'm going to get a bunch of singularities. And those singularities are going to lie inside my obstacles. And you're going to ask, will it converge? In the sense that the problem I'm trying to solve, this is a approximation to it in the following sense. On the boundary where I can make measurements, this problem is the PADI approximation of the one I want to do. And the question is, can I solve the PADI problem to get locations of these quickly? And the answer is really very fast. And then when I can do that, how does it relate to the rest of the problem? Okay. So, several stages. I get the Fourier coefficients in my data G. Then I use the Fourier PADI table to get the rational function R and Q. I've got to set some bounds in the number of poles. This problem is itself ill-conditioned. Right? You're pulling down into the interior. I need a regularization step. Once I solve for the SK as the roots, and then the polynomial in the numerator gives me the residues lambda k. So this can be done, in fact, very quickly. Okay? So this is just basically information about it's nonlinear, but you see it's only one nonlinear step in it. I'm going to show you a method for doing this Juré al-Badia and Huadong that works if you assume that the poles are all monopoles. This means that your P upon Q, the P has 1 degree less than the Q. Double roots could happen, but the chances of that are very slim. And if you avoid that, then this is a rather clever way to do things. If you do it the more general way, it's not much different. And if you've got a double root, it doesn't matter. So there's the problem I'm looking at. The real problem is to get a chi of d, which is the sum of dj's with this data. And I'm going to solve the simpler source problem. And the theorem is, this problem here, the easy one, is the PADI approximation of that one. Okay? So there's 3 steps. I get the locations of the poles and residues. Then I cluster them to try and find out where the main dj are. And then I'm going to solve a nonlinear moment problem to recover the geometry. So that's the plan. So here's how it goes. You inner product your data G with cosines and sines, you get the Fourier coefficients alpha j, and that happens to sticking into the equation that gives you this. Well, you can say, well, this is ridiculous. I've got too many things here. But you're going to measure actually 2m Fourier coefficients, and you've got exactly 2m unknowns, residues and poles. So the diagonal matrix D has the pole locations in the diagonal entries. You've got a vector, and you form this matrix, AJ, and this matrix B, which is Hankel. You can show that AJ plus 1 is AJ times D. That's quite easy just from multiplying. You can show that A naught is invertible. Aha! It's a van der Monte, but the poles are distinct by my assumption. You use SVD with some truncation to make sure that B is invertible. So this is the regularization step. This is where you decide how many of the poles you're actually going to get, what M is. If you've got a very singular matrix here, you have to truncate it down until you're happy with that parameter.
Wait.
Yep.
Where did the alphas come from?
Alphas are the Fourier coefficients of my data. Okay? And this is the main regularization step. So if the BJs are the columns of B, you can show this. And so there's a companion matrix that takes the columns of this matrix B, one into the other. Takes this into that, into that, into that. And the last row is given by this. And T has eigenvalues SK. And then this gives you the residues. But T is a companion matrix. Very fast solver for getting the eigenvalues of that. Okay. Connected, of course, with finding roots in the complex plane. Right? And once you've got that, then, oops, I gave you too much. Once you've got that, you can get the SKs and the lambdas quickly. Now you've got a cluster. The fact is, if you've got a monopole, or you've got a circle, center where that monopole was, and you're measuring the outer boundary, these two things are exactly the same. The strength of that monopole corresponds to the square root over 2 pi or something of the radius of that thing. Okay? Now, I'm going to convert my residues that I got into little circles. So around each of my poles, I'll draw little circles. If these circles intersect, they're the one region. If they don't intersect, they come from a separate region. So that's the clustering algorithm, and that's what that does. So now I've clustered, how do I get the moments? Well, I use Green's theorem, nothing more sophisticated. And when I use Green's theorem in its second form, and I apply it to the kth cluster, for any harmonic function h, I get this. Now I'm going to choose h, and I'm going to choose h to be pure powers. For Laplace's equation, they're harmonic. So I'm going to take h to be harmonic polynomials, and when I do that, I end up with this equation. dj is known in terms of the lambdas and my roots. And this is powers of my unknown function q. That's its Fourier coefficients are given by dj. So this moment problem is nonlinear, but it can be solved by Newton iteration, and it converges very, very quickly. Let me point out that I'm making an assumption here, going from that step to that step, the region is star-like. Okay? If I use the frozen Newton scheme, then it turns out that this derivative is purely diagonal and gives me exactly the Fourier coefficients of my unknown step up. And it doesn't converge as quickly, but you don't have to do any kind of moment problem at all, and it's still amazingly fast. So it's fast and it's transparent. So here's an example. These are 3 regions. I'm going to give you 64 data points where I've measured Cauchy data 0 for the value of u and a flux g. I'm measuring it at 64 points, and the rough value of my flux is about 0.1, 0.2. I solved it to 4 decimal places or better in MATLAB. I truncated it to 4 decimal places, and I gave it to the solver. So roughly I've got an error that's a little bit less probably than 0.1%. Accurate data, right? So when I take a very aggressive spectral cutoff, I only get 3 poles. I was worried about this Hankel matrix B, so I said, no, you can't take too many poles because I want this to be my cutoff. Well, I get 1 pole in each region, which, well, that's not very good. I disagree. I've now indicated, and look at the overlapping circles. See these overlapping circles? The clustering algorithm has a field day with this. It declares them to be all separate. So what it's going to give me now is 3 regions. It gets the location pretty well, and it gets me the size pretty well. Okay? That's what I get. All 3 are circles. Well, that's all I can do with that cutoff. So let's go to 6, 10 to the minus 6. And now I get 5. It puts 2 in each of these. The clustering algorithm has no problems. Look at this. They're definitely clustered by my no intersection trick. Not bad. And now we go to sigma's 10 to the minus 7. This is the best I can do with that data. After this, even a small amount after this, it rapidly breaks up and I get complete junk. But I now get 7 poles, and there they are. Now, the more poles that I give it, the residues here are almost real, but they're not quite. But the sum of the imaginary parts in each cluster must be 0. That helps in clustering and will be important later on when I get there. Anyway, reconstruction is pretty good. And now this is accurate data. You could never get that reconstruction using Newton's method unless you knew the answer or nearly the answer. Okay? Notice it doesn't quite resolve that. This needs more Fourier modes. Oh, no, this was terrible. Sorry. This needs more Fourier modes than I can get out of it, given there's 3 regions. And that's the best you can simply do here with that kind of level of noise. Okay, I promised you about inclusions. And why would inclusions have anything to do with point sources? Well, the answer is the point sources must be in the inclusions. And if I do exactly the same trick, I don't tell the PAD-A solver that the data that it's about to receive doesn't come from a source problem, but it comes from that, it doesn't care. And so here's what I get out with my 2 regions like this. By the way, I couldn't do 3 regions. This is not 64 points, but 96 points. To get 3 regions, I needed many, many more points. This is where U is 0. This is where U is 0. If you draw a line between these two, by the maximum principle, I've got U is 0 here, but positive flux. So you know that in here, the solution is strictly positive. Between these two, that line, the solution is never bigger than 0.01. It's very flat. And in fact, once I get these, I simply go from the centroid of them out radially to the boundary in both cases, and I look for the level sets. And here's my level set finder. This is bad here because it's very flat. It's good here because there's still a good slope coming in from the boundary. But here, quite poor. Of course, I don't believe that's what I have. This is hardly a convex function, or it's hardly even what you might call a smooth function. So I'm going to make it smooth by penalizing against convexity, or sorry, against curvature, and then you get a pretty good reconstruction. But even if I just simply live with my poles here, and I draw circles around them with the right location and give it to my Newton solver, there's a good chance that it'll do something for me. However, there are lots of problems here that I've glossed over, okay? But I want to go on. So these are intrinsically 2D things. I'm in a complex plane. But you can use projections of 3D into the 2D slices, and you can do it 3 times, and then you can combine the algorithms to actually, at a fairly modest cost, do 3D reconstructions of my sources. Okay? But the restrictions to the Laplace's equation come through the fact it's an analytic function, harmonic function to analytic function, and that fails, for example, for the heat equation. So I can't apply this to getting source terms in the heat equation. How about for the Helmholtz equation? Well, again, there's no hope to try and get the same thing because you're losing analyticity. Helmholtz solutions are real analytic of the 2 variables, but not complex analytic of a single variable. Clustering might adapt, and then the conversions of the poles to the geometry will have a similar formulation. Instead of putting in test functions that are harmonic polynomials, I'll put in Bessel functions. They're almost harmonic polynomials plus a perturbation term. Okay? So, the trick is, take the Helmholtz data and just give it to the PAD-A approximation scheme. It thinks it's solving for Laplace's equation. Okay? Now, when you've got the location, you don't solve for the poles of Laplace, you solve it for that van der Monte gets replaced by powers into Bessel functions, and that gets you the monomial for the residuals. So that's already using, this is using Laplace, but this is now using Helmholtz to update. Then I solve the direct problem for the poles for both Laplace and Helmholtz, getting these things, and then give a correction term like this, and then throw it back in again and repeat. The clustering is almost exactly as the Laplace case. The residues for the Helmholtz equation or more, have a larger imaginary part. If you just simply take the modulus, then you get a very good approximation to the clustering algorithm working unless the two regions are very close together. Okay? And then the Newton scheme works exactly as before, but the moment problem gets Bessel functions in the kernel rather than powers, right? But it also works. So here's what happens. I gave it data, and the real locations are the black ones. That's where the real poles are. Okay? I gave it that data to the PADE solver, and it thinks it's Laplace, and there's what it gave me instead. So they're not the same, as you must expect. Kappa here is 1, so it's not small. Kappa is 1 is actually higher frequency than the resonance region, because the resonance region is somewhere quite smaller than that. So this is quite a large kappa. Okay? If I use the iteration scheme, here's what happens after I iterate just once. Really much closer. And in fact, after you've got 2 or 3 iterations, there's no point in continuing. You don't need to get an exact location of these things for it to work pretty well. And there's a reconstruction. Now, quiz. Remember our problems here? This is better. This is a better reconstruction even than I got for Laplace's equation. Why? The Helmholtz equation is a lot better posed than Laplace's equation. The frequency k, the higher the frequency, the better well posed it is, the lower the frequency, the worse. So I'd expect to get better reconstructions here, and I do. So let me finish off by telling you that the Helmholtz, by the way, can I prove the convergence of that routine that goes from the Helmholtz to Laplace and back again? The answer is yes. But there's a famous line, well often quoted in theorems like this, for small enough kappa. There's a reason why I can't expect the thing to converge for large kappa. You just saw the previous picture. The large kappa case is much smoother than the Laplace. When I give it the Helmholtz data, it tries to get Laplace points. It tends to give me less Laplace points than I think I deserve for the Helmholtz. And this is why the algorithm does work. I'm actually computing a more ill-posed problem, the PADE, than the actual one I have. But what can sometimes happen as you're flipping from back and forward, it can adjust the number of poles that is coming out. And that's to be expected, right? And it doesn't happen, I've never yet had that problem if kappa is less than 1, but if I run kappa up to the maximum, which is about 2.4, and near it, then it starts to happen all the time. Okay? And so I get 5 poles out, next iteration it says I've got 6, and it goes down to 5 again, and convergence here is not going to work, right? So it's not without difficulties, but it's stunningly fast. Okay? I've got 7 poles. Remember what I had? I had to do what? I had to solve, invert a 7x7 Hankel matrix using SVD. I had to find the roots of a companion matrix, size 7. That was it. Oh, and a Van der Monte, size 7. When you're solving 7x7 matrices in the 21st century, everything's fast, right? So this is lightning fast, this step. The clustering is really fast unless it's difficult, right? And the moment problem is just a couple of integrations, actually. So this is nanoseconds in any reasonable machine. Okay, but the Helmholtz equation has got a new feature. What if I didn't know the strengths of each of the regions dj? That is, f was some constant sigma j times chi of dj. So some have strength 2, some have strength 1/2, some have strength near 1. Well, the answer for Laplace's equation is dead simple. It isn't possible. Right? There are, in fact, lots of counterexamples. So no, you can't do this. But in the Helmholtz case, what if I decide to give you two measurements, either far field or Cauchy data, from two different frequencies? It actually works. Now, let me tell you what we can't prove. We cannot prove that this works. What we can prove is that when you put the two frequencies in, you get a system of two equations. When you linearize the leading term, you can show that that leading term around about any circle of radius r has non-vanishing determinant. And you can get an estimate on it. In fact, the condition number is exactly this. Now, this looks pretty good. But remember, r is the radius of one of my regions. Those little regions there are about somewhere between 0.115. Right? They were 0.3 in diameter. Well, even if r is 0.2, then there's the condition number, 10 to the minus 4 times the difference of the frequencies, if the frequencies are roughly 1. More frequencies don't help, just the maximum distance between them. Right? So there's no point in giving me 10 frequencies here. I'll just choose the one with the largest spread, and it won't be any difference. So this only really works for the sigma j not too far from unity. And if I don't do this, and I hope for miracles, you're going to have problems clustering. The clustering algorithm, right, took the equivalent circle. But if I'm looking for that equivalent circle with chi of d, that is sigma 1, and it turns out to be 5, then that clustering algorithm falls apart immediately. Okay? And there's no way to tell. So this is really only going to work for the sigma j's not far from unity. But if you do that, then you get pretty decent reconstructions. Okay? I don't have a picture to show you. It's not as good as the one I just did, if I've got two kappas, because you're putting some of the energy of the process, the information content, into this piece. And this is a real limiter. Okay? But you can certainly do that. There's many more things I could tell you, but I think I'm ready for coffee, and I know that you are too, and I thank you for your attention.
Questions?
Sorry, I misunderstood. Period some s lambda k s k on the right hand side.
Yep.
And then s appeared as a numbers.
Okay. Now, I can do this two ways. I can hope that with a bit of luck I can get back without going too far. We're getting there.
Yeah,
Okay.
but page before. Page before. Yeah.
Okay.
Sk here.
So I've got f here. The f function itself is the sum of regions dj, where it's 1 in dj and 0 outside. Right? The fs is given by this. These are delta functions. So these are delta function poles, residues lambda k, sk the location. Okay? I'm trying to get lambda k, sk. Okay? Once I get
So
these,
Sk is not a surface, Sk is
sk is
a
the
number.
is a number.
Complex number.
Yeah, complex number.
So is it a plane? Yeah.
Yeah.
Okay, complex number.
And I've got alpha j, I've got 2m alpha j's, remember, and I've got 2m unknowns. Everything's complex. Okay? So this of course couldn't possibly work for the Helmholtz, right? But I'm never solving the Helmholtz, I'm only doing it for Laplace, and then that correcting piece. And then this is the relationship I got here, and this Hanko matrix is the standard Hanko matrix for solving pi-day problems. And
So, sorry, Return to the previous page, yeah.
Go back again.
Yeah, yes. So what do you know? What is the known data? This is
What I know is
cache
this.
data. You
This
know
is
cache
the
data.
only thing I know.
Cache data. J.
Cauchy data.
J.
So I use the Cauchy data, and I say I've got an analytic function with this Cauchy data. Is it metamorphic? The answer is it has to be, because it's a singularity from the original problem. I'm assuming, because I'm making this ansatz, that it's metamorphic. It's got a Paddy approximation of size this. Now I tell it to go find the Paddy approximation to that data. And it's going to return to me the lambda k and the location sk. Okay? And this process here is simply the mechanics of doing that. I'm going to invert this b, I'm going to invert a naught, and I'm going to find the roots of this companion matrix. They're all of size m, and m is way less than 10. If you actually want 10, I did some experiments, you have to give me data that's accurate at least to 10 to the minus 6. I mean, of course you can do this, you want m to be 100, you just give me more and more accurate data. But I made a cutoff, was what I said, and the answer is 7 for that cutoff, right, of what you can get. So this is really, really fast. And it's simply solving 3 matrix standard matrix problems.
But sorry, but this is maybe I misunderstood something. But cache data is incorrect data for class equation. So the
Well,
solution on
The Cauchy data is the incorrect data for this ansatz. The G is the G from here. But this is simply an algorithm, right? And I'm going to give the algorithm a function G and ask what does it put out. What does it do? What this is just showing you is there's an underlying analytic function U, harmonic function U extended to an analytic function, outside of my domains D. There must be some kind of singularity inside. Okay. I'm going to make the ansatz that singularity is coming from poles. And I'm going to do that by taking the nth order Paddy approximation. And I'm saying that the solution of this problem is approximated by the solution of that problem. And in a well-defined sense that that's true is that the solution I'm getting from this, the function U extended to an analytic function, is the Paddy approximation of this.
So, Bill, I have in mind a practical problem somebody asked me. They were
Oh no!
they were in the nuclear industry and they were doing inverse thermography. So they had some radioactive nasties generating heat in a tank of water, and they had a thermal camera, and they could interfere by imposing Cauchy data, which amounted to cooling it, so they could fire a water jet where they wanted. So they were set up to do this problem in 3D, and so you did say somehow you could have an approximation of the 3D problem by solving
If you do
3D. What would you do?
What you do is you look for the points by you find the projections of the points on the XY plane, taking the XY plane data.
Yeah.
So you project the data down onto the XY plane, and you get the locations of the poles in the XY
So
plane.
you project the Cauchy data?
Yeah. Put it onto the XY plane, solve the problem now in the XY plane, and you got the poles. Do it on the XZ.
But you take the average of the Cauchy. You take the average of the Cauchy data?
Yeah.
Right. Okay.
Do it on each of these 3 things,
Yeah.
and then project up.
Yeah. Sure.
It's not an order of magnitude faster to go from 2 to 3.
Yeah.
It's you've got to do the problem 3 times, and then just a projection problem to get the.
And then the
points.
fitting. Would you then, when you find the poles, do the fitting stage in 3D? Is that the idea?
Right. Now, the clustering algorithm works just as well in 3D,
Yeah. Yeah. Sure.
right? The moment problem there is only about the radial part of the ring. That's the assumption of star-like. So the moment problem is exactly the same. Nothing changes.
Okay.
So it really does work in 3D, or any number of Ds you want.
Any other questions? Other further discussion on coffee?
No, there is
Here?
Can you see the number of obstacles?
I can get you 7 poles with data that's order this accuracy. So those 7 poles, that's it. If you happen to give me a bunch of circles, how many circles could you give me? 7. Right? If you want to give me one that's not a circle, to get any geometry out, you have to have 2 poles in there at least. So if you want to do that, you can give me 5 circles and something that's not a circle. If you want none of them to be a circle, then you're down to at least, well, no more than 3, right? Because you need 2 in each one. So the limiter is simply the information limiter, and that limiter comes in by your estimate of your data and the SVD or whatever regularization step you want to do, cut off on the Hankel matrix inversion. That's what tells you the number of poles you can get. And I'm telling you the answer with roughly accuracy of 1.1%, you can get about 7 poles max.
So, but you assume that your boundaries of the domains are smooth?
On the outside?
No, inside.
Oh yeah. Oh yeah. It's star-like too.
So, but if there will be any cusp there, can you see it?
Okay. Think about it this way. You've got 7 poles, 7 Fourier modes, and you want to get, let's say, 3 regions. One here, and this one you want to have a jaggy boundary, right? Hold it. With 7 poles, if you put 1 here and 1 here, or that's the way it comes out, you've got 5 here. You've got 5 Fourier modes to get that boundary. How well can you get a complicated boundary with 5 Fourier modes? You can't. And if you put 2 here and 2 here, you've got 3 here. It's just really the law of conservation of information.
I didn't understand, why does it get better if you use the Helmholtz in the approximation of the shape?
Because the Helmholtz equation, if you look at the source problems, or if you to try and, let's suppose you did the Newton scheme that I mentioned with a good starting guess. When you look at the Fréchet derivative as a function of kappa, right, the ill conditioning of that is a strong function of kappa. As kappa goes to 0, right, in fact for the Helmholtz equation it blows up, and you have to use Laplace separately, but as kappa goes large, then you've got good conditioning. If kappa's large,
distance to eigenvalues.
right, but forget the eigenvalue problem. If kappa's large, you're using exceedingly short wavelengths, and you're basically firing rays at this thing, and you get good resolution. If you're firing long wavelengths, right, small kappa, then you get poor resolution. Okay? And the worst possible case is to go to the limit of 0 in Laplace's equation. Okay? The reason this works, but the reason it's not optimal, is I'm not solving the Helmholtz equation, ever. I'm solving Laplace, and then adapting those points to solve the Helmholtz later on. So I'm using the Laplace inversion scheme through that PAD-A. The reason that it works stably is the Helmholtz is better, and I'm making it using the base limit or something worse. If it was the other way around, I wouldn't get convergence. But on the other hand, you could argue it's not optimal, and I'm not taking advantage of what might be the best data for the Helmholtz. I concede that.
Sorry, I still misunderstand.
Can we write it down over coffee? No, I'm not putting you off. I mean, no.
Yes. No, I don't think,
It's 10 past.
yeah, it is 10 past. Perhaps we ought to adjourn the sort of formal part of the talk but I'm sure that Bill is quite happy
Yeah.
to continue discussing this.
Like a different.
I want to ask, let's thank the speaker first. And then I want to